Today's lesson is on intermolecular forces, and a lot of times we'll just call those IMFs. In the past, we've talked about intramolecular forces. Now, those are going to be the attractive forces that are within a molecule. So that's basically what's holding like a carbon dioxide together. So that's what we've got right here, attractive forces within a molecule. And again, this is what's holding the molecule together. Now, these are going to be the three big ones that we talked about really at the beginning of the year. So we've got ionic, covalent, and metallic. So let's go over those real quick. First off, ionic is going to be a bond that forms between a metal and a nonmetal. Now, this bond happens because of the big difference in their electronegativity. And so we've actually talked about that back when we did periodic trends. So high difference in electronegativity. I'm just going to put E in for electronegativity. Next, we've got covalent. Now, covalent is that bond that forms, I guess this should be forms, between a nonmetal and another nonmetal, or just nonmetals. And this bond happens because of the low difference in electronegativity. It's a long word. Lastly, we've got our metallic bonds. Now that does, again, that's exactly what it sounds like, bonds that form between metals. Bonds that form between metals. Now, remember with your metallic bonds, that's going to be a sea of electrons. So those electrons are free to move about the entire molecule and all of the ones that are nearby. Okay, so that's intramolecular forces. Again, that's that internal bond in those molecules. Today's lesson is about intermolecular forces. So intermolecular forces are the attractive forces between two molecules. So I've got one carbon dioxide on the left, I've got another carbon dioxide on the right, and it's the bond that forms between those two carbon dioxides. So it's between two molecules. Now, this is what's going to hold one molecule to all the molecules that are surrounding it. And it does vary in strength, but they are actually always, I've got generally here, but I'm going to change that to always are weaker than the intramolecular forces. And that kind of makes sense, right? So if I've got a intramolecular force that's holding a carbon to an oxygen, that's going to be weaker than what's attracting those two carbons or those two oxygens and carbons that are on a molecule beside it. Now, in our intermolecular forces, we do have three types. We've got first, London dispersion forces. Second, we've got dipole-dipole. And third, we've got hydrogen bonding. So let's start with London dispersion forces. Now, these are a little bit strange. So in a minute, I'm going to show you all a video to kind of show you how that happens. But what they are is a temporary attractive force. So these are temporary attractive forces. Let's see if I can remember how to spell things. Between all molecules. Now, this one is all molecules. So anytime we've got an intermolecular force, there's going to be London dispersion forces that are happening, LDFs. And it is in every type, both polar and nonpolar. So all molecules. So polar and nonpolar. Now, again, this is in, and nonpolar. This is in all types of bonds, all types of intermolecular forces. Next, we've got dipole-dipole, and these are the forces between polar molecules. Forces between polar molecules. And lastly, we've got hydrogen bonds. And these, again, are forces between polar, but it's a specific type of polar. So forces between polar molecules. But specifically, it's going to be a bond with a hydrogen bond. Well, let's erase that. Write it down here. It is a hydrogen bonding with a nitrogen, oxygen, or fluorine. All right. So a nitrogen, oxygen, or a fluorine. Now, again, this is a bond between polar molecules. So hydrogen bonds are actually a type of dipole-dipole. Okay, so it's a type of dipole-dipole. And I'm actually going to highlight that. Type of dipole-dipole. All right. Now, for this, you do need to know what type of intermolecular force, what type of IMF is going to be happening. So ultimately what it comes down to is polarity. So if you remember back when we were doing Lewis structures, one of the things that we did was we were determining the polarity of the molecule. And so that's what we're going to have to do with this. So just do a quick rundown of how to do this. The first thing is you're going to need to write the formula for it. So if it says it's carbon dioxide, you would write CO2. Next, you draw the Lewis structure. I'll go over how to draw those Lewis structures here in a little bit, just as a reminder. Then you draw the shape. Okay, so you're gonna need to determine your VSEPR shape. That is very, very important for IMFs. After that, then you're going to have to figure out the difference in electronegativity. We're going to use the general trend since you're not going to have access to an electronegativity chart. So remember that trend is we start at fluorine. Okay, so we're going to start at fluorine. And then if we're moving left, you're going to change your electronegativity by 0.5. So it's going to decrease by 0.5. And as we move down, it's going to decrease by 1. So again, as you move left from fluorine, you're going to decrease by 0.5. And as you move down, you're going to decrease by 1. All right. After you have figured out what your electronegativity is, then you would draw your electronegativity arrows depending on what you've got. So remember with that, if it is ionic, which is a type of polar bond, right? If it is ionic, you're going to have a difference of electronegativity greater than 1.69. Okay, so if you subtract fluorine and hydrogen, fluorine is a 4, hydrogen is a 2.1, their difference is 1.9, so that would be an ionic bond. For covalent, you've got two types. You've got polar and you've got nonpolar. So if it is a polar covalent bond, your difference is going to be from 0.4 all the way up to 1.69. And then if it is a nonpolar covalent bond, then that's going to be basically less than 0.4. So less than 0.4. Okay, so 0.39 and below. All right, once you've got your arrows drawn, and remember those electrons are going to be moving towards the one with higher electronegativity. It's attracting those electrons towards it. After you've drawn your arrows, then you're going to label your positive and your negative side. Here are the symbols that we use. So if it's the positive side, we're going to use that. And if it's the negative, we're going to use this. And I like to think of that as like a slightly. So I would say this is slightly positive or it is slightly negative. Okay. Once you've done that, you do need to again know your Vesper shape, but then that's where you're going to determine if it's going to be polar or non-polar. All right. So let's actually talk about some ways that you can recognize your intermolecular forces. So an easy way to immediately know what type of intermolecular force is at play is if you see that that molecule is non-polar. All right. If it's non-polar, the only type of IMF that's involved is going to be your London dispersion force, your LDF, London dispersion force. That's the only type that's nonpolar. So if you see that your molecule is nonpolar, you automatically know that that's going to be an LDF. Next, if you see that your molecule is polar, there are two things it could be. Probably, if it's just polar, it's going to be dipole-dipole. So dipole-dipole. All right. Now, if you notice that that molecule is polar and it's got a hydrogen bonded with a fluorine, oxygen, or nitrogen, then that's when you've got your hydrogen bond that comes into play. Now, again, remember, all of these, like if I've got a hydrogen bond, I've technically also got some dipole-dipole going on there. I've also got some LDF going on there. Okay, so they kind of work in tiers. So your hydrogen bond has all of them involved. Dipole-dipole is just going to be dipole-dipole and LDF. And then if it's nonpolar, then you're just going to have LDF. All right. So let's go over what each of those types of bonds are. I know I've talked a lot about what you do, how to figure out what they are. So let's actually look at what each individual substance or type of intermolecular force is. So I've got London dispersion forces. Now, again, this is going to be the attractive forces that form between nonpolar molecules. And so I'm going to read through this real quick. So the protons of one nonpolar particle attract the electrons of another nonpolar particle. When the electrons move over to one side of the molecule, it will cause that one side of the molecule to be slightly positive and then the other side to be slightly negative, but that's only temporary, right? So kind of confusing. So let me actually show you a video of this. So here we've got a molecule. This is helium, right? Because we've got two protons there and we've got two electrons floating around it. So as this is going, and I've got that linked in the previous, as this is going, one thing I want y'all to recognize is, all right, so look right there. So electrons are constantly moving around and they're very, very fast. And sometimes we will see where those electrons kind of line up. And so what that is that's a temporary dipole. So right here, you've got one side that's going to be slightly negative. So that's going to be up there where those electrons are. And then the other side where your protons are, that's going to be positive. Okay, and then as those electrons keep moving, that dipole goes away. And then they're going to keep on going. Again, you've got those electrons constantly moving. Again, temporary dipoles are being formed. Eventually, you're going to have it match up. And so you've got your weak attractive force that happens because you've got your electrons on the left side on one substance, which means you've got your protons on the right on the other. So hopefully that helps. There are these two videos that are right here. These two are basically what I showed you. They're just visualizations of how the LVFs occur. Basically, those electrons keep moving, and they're going to form that temporary dipole. And then when they eventually keep moving past that, that dipole goes away, and that intermolecular force slowly deteriorates. Next, we've got dipole-dipole. Now, this does occur between polar molecules. So the partially positive end of one molecule is attracted to the partially negative end of another. So here's a video of that actually occurring. So here I've got two molecules. So if you notice, you've got your positive end on the left and the negative end on the right. And you've got this other molecule that's slowly coming up towards it. Now, if you notice, when you get your positive ends together, they would repulse, right? So it got close, and then you notice it kind of bumped away from it a little bit because they're going to be repulsing each other. But then it's going to be attracted to that negative side, and then that's where you see that dipole-dipole form, that intermolecular force between polar molecules. All right. Last, we've got hydrogen bonding. Again, it's basically the same thing as a dipole-dipole, but with that, you're going to see a hydrogen, and it's bonded with a nitrogen, oxygen, or a fluorine. Okay. Now, sometimes you're going to run into something where you see that there's two intermolecular forces and they're the exact same, and I'm asking you to tell me which one is stronger or weaker. If that's the case, then you're going to look at your molecular weight. Okay, so the molecular weight, the heavier the particle, the stronger the IMF. Now, again, this is only going to be, and I'm going to highlight this in a different color, it's only going to consider this if you're comparing IMFs of the same type. Okay, so don't look at two substances and see, okay, well, this has a higher molecular weight, so it's obviously going to have the stronger IMF. The only time you can do that is if they are the same. Okay, so let's actually go through and solve one so you can see what type of IMF is formed and what kind of structure it makes and all that stuff. So we're going to go over that. I'm going to walk you through every little thing. So I'm going to zoom in right here and just kind of do a recap of what you need to do when you're solving for a Lewis structure. So the very first thing that you need to do is you need to count your valence electrons. So count your valence electrons. So here I've got CH4, okay? Carbon has 4 valence electrons, okay? And there's only one of them there, so there's 4 there, okay? Then I've got hydrogen. Remember, each hydrogen has 1 valence electron, but there's 4 hydrogens present, okay? So when I add all that together, I have a total of 8 valence electrons. Okay, again, carbon has 4 valence electrons. You can find that by looking at a periodic table. You can use either the ones that we gave you at the beginning of the year, or you can go online and look up a periodic table for that. And then hydrogen does have 1 valence electron. It's in the first column times the 4 that are present. Okay, so you've got 4 present. That comes from that 4 that's right there. Okay. Second step is to pick your central atom. All right. Now, when we look at this, our central atom is going to be carbon. Typically, the easiest thing to do when you're picking your central atom is to see which one you have fewer of. That's more often than not, that's going to be the one that's in the middle. So carbon. Okay. Now, I spread everything out. Okay. So I like to spread out everything else. Misspelled that. So spread out all others. Okay, so here I've got 4 hydrogens, so I like to spread them out as far as possible. I'm going to pick the top, right, bottom, and left. Okay. After we do that, we connect them to the central atom. I'm just going to put central. Okay, so we form that one bond there. And we're going to be figuring out what type of intramolecular force that is in a little bit. Okay, next step is to fill the outer octet. Okay, now remember your rule with your outer octet is, or with all your substances, there are some exceptions. Hydrogen is okay with 2. Beryllium is okay with 4, and boron is okay with 6. Hydrogen's okay with 2, beryllium's okay with 4, and boron's okay with 6. Everything else needs to have 8 in its outer octet. Okay, so looking at our CH4 here, if I'm looking at my hydrogen, so let's say that hydrogen right there, okay, hydrogen has how many attached to it? Well, it's got this right here. So that one right there represents 2 electrons. So that hydrogen is okay. All right. Let's look at the next one. That hydrogen, well, that hydrogen, and we've got 2 electrons. Same thing with all of those hydrogens there. Okay. Next thing is to count up. So count all your electrons. Okay. So I've got 2 electrons there, 2 electrons there, 2 electrons there, and 2 electrons there. Okay. So that's a total of 8 valence electrons. Well, if we look back over here to our initial count, we're supposed to have 8 valence electrons. So that is correct. Next thing would be to check our central atom. Okay, so check your central atom. You need to make sure that your central atom is, again, filling its octet. So again, if it's hydrogen, it should have 2. Remember, hydrogen should never be in the middle. Beryllium should have 4, and boron should have 6. Well, since it's not any of those, then it has to have 8. So let's check this. Carbon has 2, 4, 6, 8. So it does have 8 valence electrons. Okay. So count your electrons. Check your central atom. Make sure it's good with its number of valence electrons. And then once you've done that, now we can start with our Vesper shape. Okay, so looking at our CH4, sorry, I'm trying to scroll over, it's not letting me. Okay, looking at our CH4, can I spread those molecules out anymore? The answer is no. So that shape would be tetrahedral. And it's basically going to maintain this shape that we've drawn, right? If we go a little bit more 3D, we'd know that they would spread out a little bit more. So that's basically a tetrahedral. So now we need to check our differences in electronegativity. Okay, so first off, if we count over from fluorine, we find that carbon has an electronegativity of 2.5. So carbon is 2.5 for its electronegativity. Then we count over to our hydrogen as you're counting over, and then you go up, you'll find that hydrogen, just with your counting, would be 2.0. Hydrogen's technically a 2.1, so that's what I'm going to put. Okay, and we find the difference there. So their difference in electronegativity is 0.4. Okay, well, if we think about our rules, this is going to be a polar covalent because, again, it's going to be greater than that 0.4 or 0.39, and it's going to be less than 1.69. Okay, so this is a polar covalent bond. Okay, so if it's polar covalent, that means those electrons are going to be moving in a direction. Okay, in this case, since carbon has a higher electronegativity, those electrons are going to move towards carbon. So in that direction. Now, when those electrons move towards carbon, that makes the hydrogen side positive. So we would put our symbol of slightly positive. We check all the others. They're all the same type of bond, right? So they're going to all do the exact same thing. Okay, so slightly positive on all of those. Okay, now all those bonds are polar. So sometimes you're like, okay, well, that means the molecule has to be polar. Well, let's look at the molecule. Remember, to be polar, you need to have one side that's positive and one side that's negative. Here, we've got positive, 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 and positive. All the sides are positive. So what does that tell you about your molecule? Well, it tells you that it is a non-polar molecule. So the polarity is non-polar. Okay. Well, if the polarity is non-polar, if we think back to our rules with IMFs, the easiest way is if you see non-polar, you immediately know that the intermolecular force, the IMF, has to be LDF, or London dispersion forces. Okay, and either of those answers are acceptable, LDF or London dispersion force. Okay. All right, so let's do another one. Let's try a different one. So here I've got water. Okay, again, our first thing that we would do would be to count our valence electrons. So I've got hydrogen. Hydrogen has one valence electron, but there is two of them, so times 2. I've got oxygen. It's got 6 valence electrons, but there's only one of those there. Okay, so we have 2 plus 6. We have a total, again, of 8 valence electrons. Next thing to do would be to pick our central atom. Okay, so our central atom is going to be oxygen. Then we're going to spread everything else out around it. So our hydrogen and our hydrogen. And we're going to bond those with the central atom. Okay. Next step would be to fill our outer octet. Okay, so our outer octet, remember, everything wants to have 8, with the exception of hydrogen, beryllium, and boron. In this case, again, we have hydrogen. Okay, so hydrogen is okay with 2 valence electrons. Currently, it has 2 valence electrons. So since it has 2, it is okay. Same thing with this hydrogen here, 2 valence electrons. Okay, because again, remember that bond means they are sharing those electrons. Okay, well, let's count up our electrons and let's see how many we have. So I have 2 right here, and I have 2 more right here. So I have a total of 4. Well, I need to have 8 right here. So I haven't met that number. Okay, well, if you remember our hint is everything weird happens on the central atom. So if I've got extra electrons to give, they're going to go on the central atom. So that's what I'm going to do right here. 1, 2, 3, 4. Now, if you know, I typically don't do 1 on top or 2 on top and then 2 on bottom, because if you remember, there is that repulsion that happens with your Vesper shape. Okay, so if I were to redraw this, I would redraw it like this. You've got your oxygen with the valence electrons bonded with it. And those are going to push away from those 2 hydrogens. Okay, and so this is the shape that we would actually get. Okay, so bent. All right, so now I need to check my electronegativity difference. I've got hydrogen. Hydrogen has an electronegativity of, again, if we count over and count up, it's 2, but hydrogen's technically a 2.1. Oxygen has an electronegativity of 3.5. Again, we're just counting over from that fluorine. So your difference is 1.4. Okay. Again, this is a polar covalent bond. Okay, so those electrons are going to be moving towards one over the other. Which one are they going to move towards? The one with the higher electronegativity, which is oxygen. So electrons move towards oxygen, which means this is slightly positive. Okay, well, so this slightly positive. Same thing over here with this other hydrogen. Slightly positive. Okay, well, if this end is positive, they've pushed down and away, right? So that actually makes our oxygen slightly negative. Okay, so looking at this, we've got one end that's positive and one end that's negative. Okay, well, that makes this a polar bond and a polar molecule. So I need to figure out what type of LDF or intermolecular force is involved. Okay, well, remember LDFs are always involved, right? But we're a lot of times asked what is the most, what's the strongest intermolecular force? So let's look back here. So I know it's polar. So if it's polar, it's either going to be dipole-dipole or it's going to be a hydrogen bond. Okay, well, I'm going to redraw this. So I'm trying to figure out what is going to be bonding with what. So I've got hydrogen. Again, this is slightly negative and this is slightly positive. If I had another water molecule, would the hydrogen bond with the oxygen? Or would the oxygen bond with the oxygen? Well, looking at this, your hydrogen is positive, so it's going to bond with that negative for the oxygen. Okay, so I've got a hydrogen bonding with an oxygen. Okay, so thinking back at our rules, hydrogen bonding occurs when a hydrogen bonds with a nitrogen, an oxygen, or a fluorine. Okay, in this case, it would be a hydrogen bonding with an oxygen. Okay, so hydrogen bonds with oxygen, which makes this a hydrogen bond. Okay. Next, I want y'all to work this problem before I do. So I'm going to give y'all a little bit of time to work that. Pause your video and then I will work it through once you have finished. Okay, so you should have finished working through that HF. So let's actually do a quick, I'm going to work through it very quickly. So I have hydrogen. It's going to have 1 valence electron. Fluorine has 7. We've got a total of 8 valence electrons there. Okay, pick a central atom. Since there's 2 things, there can't be a central atom. So hydrogen is going to bond with fluorine. Next, we fill our outer octet. Well, hydrogen, if you remember, is okay with 2. But fluorine needs to have 8. So we need to put 6 more electrons on our fluorine. Count everything up. I've got 2, 4, 6, 8 on the fluorine. And then there's that bond between that hydrogen and that fluorine. So we've got a total of 8 valence electrons, which is perfect. Okay. Next, I need to do find our difference. Next thing we need to do is find our difference in electronegativity. So fluorine, we know, has an electronegativity of, 4, and hydrogen has an electronegativity of 2.1. So our difference is 1.9. Now that is going to be an ionic bond, which means it's going to have polarity that's involved. Okay. Now ionic are going to form polar molecules. Okay. So then I need to figure out what kind of intermolecular force happens. Okay, so I've got hydrogen and I've got fluorine. I've got a hydrogen side, which is slightly positive, and the fluorine side, which is slightly negative. Okay, well, what's going to bond with what? Well, the hydrogen is going to bond with another fluorine. Slightly positive. It's bonded with a fluorine, which is slightly negative. So then we get this attractive force between the fluorine and the hydrogen. So then I need to figure out what type of IMF it would be, which would again be a hydrogen bond. Okay. All right, almost there. So next I've got, what does it mean to have a strong IMF? Well, IMFs affect all sorts of properties about a molecule. Here's what stronger IMFs mean. So for your stronger IMFs, if you've got a stronger IMF, that means you've got a higher melting point, a higher boiling point, a lower vapor pressure. Okay, well, vapor pressure is basically just how much pressure is exerted when something evaporates. Okay, because those molecules are going to add some pressure to the air. Okay, higher viscosity. Okay, viscosity is how likely something flows. So it's because those molecules are going to be attracted to each other. Their viscosity is also going to be very high, which means they're not going to flow easily. So a lot of times people talk about something like oil with this, where oil flows very slowly, versus if you compare that to something like rubbing alcohol, where it pours very, very quickly. Okay, so viscosity is how easy it flows. Surface tension. Surface tension is going to be the energy that's holding those molecules together. So for that, like if you take some water and you drop it onto a table, that's the reason that the water beads up. Those molecules are attracted to each other, so they actually pull together. Okay. A challenge I'll give you is to find a penny and a dropper and some water, and to see how many drops you can actually put onto that penny. Okay. The highest I've seen is 54 drops dropped onto a penny. Okay. Next, I've got higher heat of vaporization and fusion. Both of those were back when we talked about thermochemistry. Heat of vaporization remembers that energy that's required for something to boil or condense, versus heat of fusion, which is something that's required, the heat that's required for something to freeze or melt. Okay. Last thing, we've got volatility. Volatility is basically how likely something is to evaporate. Okay. So if you've got a high IMF, that means you've got a low chance of evaporating easily. It basically comes down to your boiling point. A stronger IMF means you've got a higher boiling point, which means you're going to be less likely to be volatile. So if I've got a high vapor pressure, your boiling point is going to decrease, and the volatility is going to increase, which means your surface tension is going to decrease. Okay. So would sulfur dioxide or sulfur trioxide liquids have a greater surface tension? So to figure this out, you need to look at your IMF. Okay. So I have sulfur dioxide. I need to draw the Lewis structure for it. Okay. So I have sulfur bonded with oxygen and another oxygen. You fill your outer octets. Okay, but when I added this up, I found that this had 18 valence electrons. Okay, 6 for the sulfur, and there's 2 oxygen, which each had 6. So 6 plus 12 is 18. Okay, well, I've got, for my oxygen, 2, 4, 6, 8, 10, 12, 14, 16. Okay, that's not enough. I need to have 2 more. So I'm going to put those 2 on sulfur. Okay, now I need to check and make sure that my sulfur's good. Well, sulfur currently has 2, 4, 6. Well, it needs to have 8. Well, I don't have any more electrons to give. I can't just add 2 more electrons to there because I need to have, again, 18 valence electrons. So if I need to have 18 valence electrons, I've already got those. So what I'm going to have to do is share some more from something. So I'm going to take 2 away from one of my oxygens. 1, 2. And I'm going to add those to a shared bond between it and the sulfur. Okay. Next, we would check our differences in electronegativity. So sulfur has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. So our difference is 1.0. So there is going to be that difference in electronegativity, making it a polar covalent bond. So those electrons are going to move towards oxygen. Again, it's got a higher electronegativity, so that makes oxygen slightly negative and sulfur slightly positive. Same thing over here. Move towards oxygen, which makes it slightly negative. Okay, so this becomes a polar molecule. Since this is a polar molecule, and it is not going to form a bond between a hydrogen and nitrogen, oxygen, or fluorine, this has to be a dipole-dipole. Okay, now we're going to do our sulfur trioxide. So I have sulfur bonded with 3 oxygens. Okay, we've got a total of 24 valence electrons. Sulfur has 6. Oxygen has 6, but there's 3 of them. So 6 plus 18 is 24. Fill your outer octets. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. That's 8, 16, and 24. Okay, so not quite enough there. Or we have enough valence electrons, but the sulfur doesn't have enough valence electrons. I can't add any more, so I'm going to have to take 2 away from something and share. So I took 2 from that oxygen, and I'm going to share it. Okay. Next thing, we already know, based off of this previous problem, that those bonds are going to be polar bonds. So they're going to move towards oxygen, slightly negative, which makes this slightly positive. Same thing all the way around. Okay, now if you look on this, all the sides are negative. That means even though these bonds were polar, this molecule itself is nonpolar. Okay, well, if the molecule is nonpolar, then the type of intermolecular force is LDF. Okay, so our question was, would sulfur or sulfur trioxide have a greater surface tension? Okay, so sulfur dioxide would have a greater surface tension because it's got a stronger intermolecular force. All right. So I'm going to give y'all some time to work the next two problems, and then I'm going to just show you the answers, and that will be the end of the video. So y'all take some time to work those problems. So pause the video. All right, so here are the answers to questions 3 and 4. So H2O would form a hydrogen bond, and CCl4 would form an LDF. So that would make water have a lower vapor pressure because it does have a higher IMF. And then for question 4, you've got carbon dioxide, which forms LDS because it's a nonpolar molecule. And then you've got carbon monoxide, which is dipole-dipole because they do have a polar bond that forms between them. So carbon monoxide would have the greater surface tension because it does have the stronger F. All right, y'all, that is it. So y'all are done. Hopefully, y'all have a good understanding of IMF. But if there are some things that y'all are still struggling with, please don't hesitate to email Miss Teresa or I, and we will help you out. Hopefully, y'all have a great rest of the day and enjoy your e-learning.